Hello and welcome to our new unit on carbonyl compounds. In today's lesson, entitled Synthesis and Reactions of Aldehydes and Ketones, we're going to understand the properties of aldehydes and ketones as carbonyl compounds by investigating their synthesis and key chemical reactions and addressing these learning outcomes. Aldehydes and ketones are a functional group, and they both can be categorized more generally as a carbonyl compound. A carbonyl compound being something that contains a carbon double bonded to an oxygen. So there's a number of compounds that we can actually classify as a carbonyl compound. These include the aldehydes and ketones we'll be looking at today, but also carboxylic acids, esters, and a few others. So if I draw that out, let's just introduce straight up what the aldehyde and the ketone is. So the aldehyde has the carbon double bond O has the carbonyl, but the carbonyl is at the end of the carbon chain, and then we have the rest of the molecule being what it is. The ketone, similar, but a nuanced difference where it's not at the end of the molecule, rather the carbonyl is within the molecule. So we've got alkyl group, the ketone being within the molecule. So then, like I say, carboxylic acid also contains this carbonyl group. Esters also contain the carbonyl group just being that C double bond O. But we'll look at carboxylic acids and esters in a bit more detail in some coming lessons. So just starting with the aldehydes and the ketones for today. All right, so let's get into this a little bit. So like I say, aldehydes have the carbonyl at the end of the molecule. Ketones have it within the molecule. Naming conventions. You have the appropriate carbon number name. So whatever the alkane would be, whether it's methane, ethane, propane, butane, you have that meth, eth, bute, prop, pent, oct, etc. to specify the carbon length, and then it ends in an al. So it'll be methanal, ethanal, propanal, ends in an al. For example, propanal would look like this. We would have a 3-membered carbon, 1, 2, 3, and then we would have our aldehyde at the end of the molecule like that. Propanal, add an extra carbon, butanal, so on and so forth. Now, one thing to note is sort of similar to our carboxylic acids, our aldehydes are always at the end of the chain. So it's not necessary to number the carbon because by the very definition, it has to be at the start or the end of the molecule, right? So that's going to be our carbon 1 more or less. We can represent this in a structural formula by having the RCHO. This is different to the alcohol that has the COH. CHO shows us that it's the aldehyde as opposed to the alcohol. Here's a question, straight up, pause, draw the displayed and structural formulas of butanal. Give that a go for me now, and you can check it when you resume. So there we go, I've already done a skeletal formula of butanal, 1, 2, 3, 4, bute meaning 4. If I was to do a displayed formula, we would just show all of those bonds. How are we going for space? All good. So 1, 2, 3, 4, and then we have the carbonyl at the end, which means the carbon has a hydrogen bonded to it, and that is our butanal in terms of the displayed formula. If I wanted the structural formula, I might make a little bit of space over this side. We could have CH3 and CH2, then CH2 and CHO. So the CHO shows that it is the aldehyde as opposed to the alcohol, which has COH. Excellent. Let's move on now to the ketones. Like I say, they have the carbonyl positioned within the carbon chain. So we can see that here. We've got the alkyl groups, the carbonyl is within it. When we name them, we have the appropriate carbon chain length, whether that's meth, eth, bute, non, oct, etc. And they end in -one. So the -one from the ketone. Now in this instance, we do need to specify which carbon the ketone is on because there could potentially be a number of variants, number of isomers if you will. For example, pentatone, if I go 1, 2, 3, 4, 5. So I could have the ketone on carbon 2, and that would be pentantuone. Got to specify because we could also have 1, 2, 3, 4, 5, the carbonyl on carbon 3, and that would be pentanthreone. But then all our other rules still apply. I could not have it on carbon number 4 because that would just be the same as carbon number 2. We also couldn't have it on carbon number 1 because if we had it on carbon number 1, well, that would just be the aldehyde, right? So if we had it on carbon number 1, it's no longer a ketone, it is now an aldehyde. When we are representing that with structural formula, we just have the carbon, oxygen like that with our R chains on either side. That infers that we have the carbonyl between our alkyl groups there. Let's practice that. Can you pause, draw the displayed and structural formulas of propanone and pentanethreone? Do that now and then check. Well, you might notice we don't have the number on propanone after I've just stressed the importance of having the number on propanone. If we draw propanone where we've got 1, 2, 3, there's only one potential option here. We can only have it on 2. So we don't have to say 2-propanone because there's no other option. Because if we had it on carbon number 1 or carbon number 3, that's no longer propanone, that's now propanol because that would now be an aldehyde. So like we said with our naming conventions, if we can simplify it, if there's no other options, we don't need to include the number. So the propanone for a displayed formula would be along the lines of that. And if I were to draw a structural formula of that, I would have CH3CO CH3, showing the carbonyl in the middle there. The other one was pentanethreone. Oh, I actually just did that before, but we didn't do the displayed. 1, 2, 3, 4, 5. And I said we got pentanethreone. So we got the carbonyl there, and then we fill in the hydrogens all around. And our displayed formula, CH3CH2, CO, CH2, CH3. Fill in the hydrogens. Good habits, always do the hydrogens. It's very important. Excellent. So there would be our 2 answers there. Let's have a look at the synthesis. And in fact, the synthesis, as in how we make them, this is something that we've just looked at in the previous video. We make them through the oxidation of either primary or secondary alcohols. So this will be a good recap of that, but we're also going to delve a little bit deeper into what happens in these reactions. So we saw previously that we need a oxidizing agent, acidified potassium dichromate. Upon warming will form the aldehyde or the ketone depending on what class of alcohol we have. So oxidizing is the adding of oxygen atoms or the removing of hydrogen atoms in that organic chemistry context. And what we observe in this reaction is if the oxidation occurs, we have the orange dichromate ions going to the green chromium ions. The oxidizing agent, it itself is giving the oxygen, it's allowing the other thing to be oxidized, so therefore it itself is reduced. So when we reduce the dichromate from the Cr2O72- to the Cr3+, we get the orange to green color change, and that indicates that that reaction has occurred. And we said this was a way that we can rule out tertiary alcohols. We can identify a tertiary alcohol from a primary or a secondary because they can't be oxidized under these conditions, so we'll see no color change. So let's have a look at how we synthesize our aldehydes. We do this from the primary alcohols. So if I draw this up on the board here, we've got our aldehyde being at the end of the chain. So we need a primary alcohol because that would imply that the alcohol is also at the end of the chain. So R group, whatever my alcohol is, H, H, and then OH like that. Primary alcohol, we're attached to one other alkyl group. So if I were to have my oxidizing agent, we form the aldehyde. Synthesize the aldehyde like that. Now, one thing that we didn't discuss was the idea of defining oxidation as the removal of hydrogen, and that's why we get the oxidation here. Because you can see we're going from a molecule and we're taking 2 of the hydrogens off, so therefore we have the oxidation because we have the removal of hydrogen. Now, how do we do this? We heat the primary alcohol gently and we add the oxidizing agent dropwise. However, we said that the aldehyde is capable of being oxidized further from the aldehyde through to the carboxylic acid. So if we just want to synthesize the aldehyde, we need to prevent that. So in order to do that, it needs to be distilled off as soon as the aldehyde is formed, as it can oxidize further into the carboxylic acid. And if we're synthesizing aldehydes, we don't want to do that. However, we can easily distill this as the aldehyde will have a lower boiling point than its corresponding alcohol because of the intermolecular forces that they will have. So as we're making the aldehyde, we're distilling it off, but this only has dipole-dipole, whereas this has hydrogen bonding. It's got this hydrogen bonded to an oxygen, so therefore we can have the hydrogen bonding between the alcohol molecules, but not between the aldehyde, the carbonyl molecules. So that means we can easily distill this off and collect our aldehyde product before it oxidizes into the carboxylic acid. What about our ketones? Why don't I draw a diagram for this? Ketones coming from our secondary alcohol. So we have the alcohol essentially within the carbon chain, and that makes sense because that's what our ketone has. So if I have alcohol there, H there, and then we've got two R groups. So you can see the similarities between these two. So then we oxidize and we form the ketone between, oops, this pen is very inconsistent here, like that, there. So the same thing, the oxidation defined as the removal of hydrogen, we are removing hydrogen there to get our ketone product. Now, once we form the ketone, there's no other hydrogens to remove, so we're not at risk of further oxidation under these reaction conditions. So all we've got to do, we've got to heat the secondary alcohol gently with the oxidizing agent, and because there's no more hydrogens to take from this carbonyl, unlike in the case of the aldehyde, there is an extra hydrogen to take, we won't get further oxidation, so no need to distill the ketone product immediately. We just let the reaction go to completion. Let's look at some key reactions that we can undertake with our aldehydes and ketones. We can do reduction reactions, which is essentially the reverse of these reactions. If we oxidize from the alcohol to the ketone or the alcohol to the aldehyde, then we can reduce from the aldehyde or the ketone back to the alcohol. So, like I say, the removal of oxygen atoms is reduction, the addition of hydrogen atoms is reduction. So like I say, that's going to be the opposite of the oxidation. Uses the symbol bracket H to represent the reducing agent and simplify the equation. So the same way that we've used a bracket O to simplify the oxidizing agent, bracket H, if we're adding the hydrogen, it's a source of hydrogen, we can simplify the reducing agent. Can essentially do the opposite of what we just saw, reduce the aldehyde or ketone back to its corresponding alcohol. So the same way we need to be able to identify our acidified potassium dichromate as our oxidizing agent, we need to be able to recognize certain reducing agents. The first one is this sodium tetrahydroborate. So we've got 4 hydrogens, boron and sodium, an alkaline solution of sodium tetrahydroborate. What we do is we just warm the aldehyde or ketone with the alkaline sodium hydroborate and we'll get the alcohol being made. And then the other one we need to be able to identify as a reducing agent is the lithium tetrahydroaluminate in dry ether. What you might notice about these is they've both got sources of hydrogen there, 4 hydrogens waiting to reduce the reactant. Now you might notice we've done this one in dry ether, but this one in an alkaline solution. This one, the lithium tetrahydroaluminate, needs to be in dry ether at room temperature because this is a much more stronger reducing agent that can actually vigorously react with water, whereas the sodium one is not at risk of doing that. So like I say, with these reducing agents, with these oxidizing agents, the main skill is just identifying them as either an oxidizing agent or a reducing agent, because in our chemical equations, we just very simply do the bracket H or the bracket O to represent that. So let's have a look at these reductions. It'll give the corresponding primary alcohol. So if we do the opposite of some of the reactions we just looked at, this time I'm going to start with the aldehyde. So I'm going to start with the R, plenty of space, like that. And we have our reducing agent. And then we'll always form the primary alcohol if we're reducing an aldehyde, for the same reason that we always form an aldehyde if we're oxidizing a primary alcohol. So we end up with the aldehyde reduced to the primary alcohol. Now, what you might notice here is it's a reduction because we're adding hydrogens. And what we're doing is we're adding 2 hydrogens. We're adding a hydrogen essentially to the oxygen atom to make the alcohol. and we're also adding another hydrogen to the carbon, so we need to have 2 molar equivalents of the reducing agent. So from the reduction of aldehydes, we'll always get the corresponding primary alcohol. Similarly, reduction of ketones will always give the corresponding secondary alcohol. Let's have a look at this one here. If I come back over here, and if I modify the reactant slightly, still both carbonyls, just the position of the carbonyl is different. I've got my ketone where we've got it in the carbon chain. If we do this, we are reducing to the secondary alcohol. We'll notice that we've got the alcohol with the carbon with 2 other alkyl groups. Same thing, adding a hydrogen to the oxygen, hydrogen to the carbon, we need 2 of the H's. So just be aware of that unlike the oxidation ones, if we're adding the 2 hydrogen atoms, then we need to have 2 molar equivalents there. To finish off today, we're going to look at one final type of reactions of our carbonyls, and unlike the other ones, these ones will produce the same sort of product. It's a nucleophilic addition reaction. Addition reactions can take place across the carbonyl group. We've got a difference in the electronegativity. We've got a delta negative on the oxygen atom, more electronegative. We have a delta positive on the carbon atom. That means that delta positive carbon is an electrophilic carbon, so it's susceptible to attack from a nucleophile. Nucleophile is a liker of the nucleus, so it's looking for some sort of positive charge. Our carbonyl carbon has a partial positive charge on it. So they'll both, aldehydes and ketones, will undergo nucleophilic addition with HCN. HCN being hydrogen cyanide. So we generate the hydrogen cyanide in situ. So in situ means that we are making it in the reaction vessel. So we don't go to the cupboard and pick up our vial of hydrogen cyanide. Rather, we make it from other reactants. So we make the reactant in the reaction vessel in situ, and then that's able to react with our reactants. So we make it via the reaction of sodium cyanide and dilute sulfuric acid that will then make the hydrogen cyanide, which is weakly acidic and will partially ionize in water. So what this leaves us with, it leaves us with a cyanide, which is a good nucleophile with that negative charge, and the hydrogen ions, which are going to play a role as well. This is a useful reaction. Similarly, we saw the reaction of cyanide with our halogenoalkanes, and we said that was useful because we're making the carbon chain longer. Same sort of thing here, will increase the carbon chain in our product. Let's look at the mechanism of this reaction. So the first thing we get is we get the nucleophilic attack from the cyanide onto the delta positive of the carbon atom. What would that look like? That would look something like this. So we got our carbonyl, right? Which I'm just going to generally sort of do the ketone structure, but this also applies for aldehydes. Just in the case of an aldehyde, one of the R's is the alkyl, the other R is the hydrogen, but it's the same mechanism for aldehydes and ketones, so we'll write it once and apply it to both. So we have a delta positive here, and we've got our cyanide ions with a lone pair of electrons that is able to come in, attack that delta positive, and we're going to push the electrons up onto that oxygen atom. Recalling that we are having the cyanide ions from the ionization of the hydrogen cyanide. So nucleophilic attack from the cyanide, to the delta positive carbon. So just a reminder that when you're doing your mechanisms, we've got to include any lone pairs of electrons, our curly arrows, any partial or full charges on the molecules. Then we get to the second step where we have a negatively charged oxygen atom from the intermediate. So let's draw that. So what this would do is we push the electrons up there, we've made a new bond with the carbon, so we would end up with the nitrile. And then whatever our R group is, remember if it's an aldehyde, one of those R groups is a hydrogen. And then we've got a negative charge on the oxygen. So what this can do is this can pick up a H+ from the solution, whether that's from water or whether that's from the ionization of the hydrogen cyanide. It's just going to very quickly react, find a H+, and we will form the alcohol. So these electrons, lone pair of electrons on the oxygen, come down, form the new bond with the hydrogen, and we end up with this type product, which I might draw just slightly differently here. We've got the alcohol, we're going to have the carbon, we're going to have the nitrile. I'm going to do my nitrile there. We've got our one alkyl group, the other alkyl group. Recall, if it's an aldehyde, we have one of these R's as a hydrogen. So what we form is we form this species called a 2-hydroxynitrile. We look here, no matter what kind of aldehyde or what kind of ketone we have, no matter what these R chains are, we're going to end up with a nitrile that has a hydroxy on carbon number 2. So this is our 1,2, our 2-hydroxynitrile, like that. That's the product that we make. Due to the carbonyl, the resulting group will always be adjacent to the nitrile for both the aldehydes and the ketone. The nitrile is then able to undergo further reactions. So this is where the usefulness of this reaction really comes into place, because we can very easily chuck another carbon on and then we can convert the nitrile to some other product that we might want. For example, we can do the hydrolysis of the nitrile and form a carboxylic acid. So water and acidic conditions, we convert the nitrile into the carboxylic acid and get ammonium in the form of that nitrogen converts into ammonium. Or we can have the reduction, further reduction to an amine, where we've got the nitrile, we further reduce to a amine. Notice the 4 molar equivalents here, because we're adding the 1, 2, 3, 4 hydrogens there. And that concludes our first look at our carbonyl compounds. What have we done? We've described the formation of aldehydes and ketones from primary and secondary alcohols respectively using acidified dichromate, the reduction of aldehydes and ketones using our 2 reducing agents, the reduction of aldehydes and ketones with our cyanide. We described the mechanism of the nucleophilic addition reactions of hydrogen cyanide with aldehydes and ketones. Here are your tasks for this lesson. Pause, work through them column at a time, starting from the bottom, and you will consolidate your understandings of this lesson. Thank you very much for your time. I'll see you in the next one when we're going to conclude our carbonyl compounds with a bit more of a look at our aldehydes and ketones. See you then.